touch on mass moment of inertia. Mass moment of inertia. Mass moment of inertia. Mass moment of inertia is, if you go ahead and kind of take a sneak peek at some of the back of equations on 9.9, you will see that there is an equation that looks like this. Okay, so this is the integration of this function associated using this variable, and this is the moment of inertia across or around the axis z. Okay, all right, that's what that means. Okay, now we're not going to go over this because nobody here in this class has done integrations yet, so we're not going to worry about that. Okay. So mostly what we want to get out of this section is what exactly is the mass moment of inertia, okay? So if you look at the mass moment of inertia, it says it is a measure of how hard it is to rotate something with respect to center of rotation, okay? So if you flip the page, it gives you there some figure 9.2, 9.3, and it shows you what the moment of inertia is. So if you have an object, or looks like a spherical object there with a mass m, r away from the z-axis, okay, that is, so this is a point mass, okay, on a point mass, you can see that if you go back to flip the page 275, the equation goes that r squared m. So the moment of inertia across this is r squared m. Okay, so I'm not going to go into great detail here. Obviously, the heavier or the more mass that point has, it's harder to rotate around that axis, right? And obviously, the further you're away, it's harder also. Okay, so that kind of makes sense. Okay. Why this is squared and this is not squared, we're not going to worry about that, okay? So just know that there is a way to calculate this, okay? All right, and now if you move on to, on the bottom of page 276, there are several different things. There's a disc, circular cylinder, there's a sphere, and a thin rectangular plate. Okay, you can see, you can just kind of picture to yourself what kind of things would use this kind of calculation, okay? What kind of things would have to worry about moment inertia. So obviously it's going to be rotating things, right? Mostly rotating, it's going to be rotating things, okay? So there are several different places where this could be useful, okay? Are the engineers going to know these equations by heart? Probably not. Okay, they're just going to put it into a CAD program, and it's going to go ahead and calculate what the required moment of inertia is and what you need to around that axis to support that type of thing. All right. So let's go to the example number 1. Let's go to example number 1 to see if we can figure this out. So there's example 9.1. Says determine the mass moment of inertia of a steel shaft that is 2 meters long and has a diameter of d centimeter. The density of steel is such. Okay, so let's go ahead. So we have something that looks like this, and it is 2 meters long. So this is 2 meters. And it has a diameter of 10 centimeters. So this guy here, the radius is going to be 5 centimeters, right? And the density of steel is equal to 7860 kilograms per meter cubed. Okay, so immediately you're thinking to yourself, I have centimeters here, I have meters here, I have meters here, okay? So that's gonna come into play somewhere, right? Okay, so we should go to the circular cylinder on page 277. And it says that the moment of inertia over the z-axis is going to be 1/2 m r squared, okay? Where r is this guy here, and m is the mass here, right? So what do I have? I have 1/2. Okay, so what's the mass? The mass is going to be rho times v, right? The density times the volume. So I know what the density is. And again, it is in meter cubed, so it's going to be kilograms meter cubed times the volume. The volume is this guy, right? So it's going to be 0.05 meters squared pi. And that's going to be the A, or the base, right? Have to multiply this by the height, so you multiply that by 2 meters. So you're gonna have meter squared here, and you have meter here, so these three cancel out. And you're gonna end up with kilograms, which is what you want, right? So it's gonna be 7860 times 0.05 squared pi times 2. Okay, so this is the mass. This is the mass. Okay, that is m. Now you have to multiply that by r squared, so you're gonna have to do this. I'm gonna go ahead and just erase this. And we go r squared, so we're gonna go 0.05 squared one more time. Okay. Okay, if you do that, you're gonna get what? You're gonna get 0.154 kilogram meter squared, right? Because up till here, the unit here was what? This guy's unit was kilogram, right? We verified that over here. We're gonna have a unit of kilograms over here, right? So up till here is kilograms, all right? I mean, up to here is kilograms, I'm sorry. And then this guy's gonna be meters squared, so that's why it's kilogram meter squared. Okay, all right? So that's how you run that, okay? Again, at this point, it's gonna be more or less just looking up what shape it is and just plugging and chugging into the equation. Okay. Any questions?
Yes, I have a question.
Sure.
For example, the one we just did, the volume that I put down, why is it pi over 4?
Where?
To calculate the volume.
Because they're using the diameter, right? So they have 0.1 squared there for the diameter, where we were using the radius here, right?
Oh, I see.
So they are doing 0.4 over 0.1 squared, whereas we are doing we're doing 0.05 squared pi, right? Because if you move this guy in here, it becomes 2, right? If you move the 4 in there underneath the square, so 0.1 divided by 2, which is the radius, is 0.05, and it's the same thing.
Okay.
Okay?
And I thought that was a equation that I wasn't familiar with. I was using it.
So yeah, because I mean, most people learn it as pi r squared, right? Pi r squared. So pi r squared, where r is the radius, which is going to be pi half of the diameter, right? So this is what they're doing here. So we have pi d squared over 4. And this is what you're seeing, the pi over 4 there.
All right.
Okay?
Thank you.
Good question. All right. So